Hello everybody, this is Dr. Muqaibel, and this is a quick review of random processes. If you want to have the full lectures about random processes, you can visit my website. This is just a quick review needed for modern digital communication systems. The outline of the presentation goes like this. We'll start with a quick introduction and definition of what random processes are. We'll get some idea about stationarity in terms of mean, correlation, covariance, the meaning of white sense stationarity, properties of autocorrelation function, and the cross-correlation function. That will lead us to ergodicity and some examples of random binary wave or process. So what is a random process? A random process, or you may call it stochastic process, it is represented with capital letter and then its function of time or function of a given variable. So it's capital X of t. It's an ensemble of sample functions. It's a group of sample functions together with a probability rule assigned to each one of these possible outcomes. The probability is assigned to any event associated with the observation of these given functions. So the sample function corresponds to a sample of this sample space, capital S, and it occurs with a probability of P of S. We could have infinite number of possible outcomes, or we could have finite number, capital N. Now sample functions, the function that we generate could be discrete or continuous. So we could have discrete random process or a continuous random process. Similarly, the sample function value itself can be continuous or discrete. The random process x of t denotes the ensemble function. Here it's function of time, and as we mentioned, the small letter refers to one of these possible outcomes. So let's say that we are measuring the noise level in a certain antenna or received by a given receiver. We have lots of different functions. So when I say capital X of t, it's the random process. If I define small x, then I'm taking one of these possible functions, and if I fix the time, then I'll have a vertical line, and this vertical line corresponds to a random variable. So we can think of a random process as a collection of random variables. Every vertical line represents a random process. Now, for a given one value, we get a singular number. If we consider all the possible outcomes at a given time, it becomes a random variable. So we can think of random variables versus random process as follows. For a random variable, the outcome of a random experiment is mapped to a number, while for random process, the outcome is mapped to a waveform, usually a function of time, but it could be also space or otherwise. Now, we say that the function is stationary if the probability of this observation does not change with time. So if we take those outcomes and denote the random variables obtained by observing x of t at different times, then if you look at the joint probability, the joint relation between them, and it's not changing with time, then we say that this process is stationary, or stationary in the strict sense, which means it can do the experiment today, tomorrow, or whatever time. It does not change with time. Something like this may look like stationary, but observation like this is not stationary. If you do the experiment now, you get different random variable and doing the experiment at a different time. So this shows you some samples of a random process which are not stationary. Now the advantage of being stationary, if you know that the process is stationary, you can do the experiment whenever you want. So if the noise is stationary, it means that don't worry about time. Don't worry much about time, because you could change your experiment time. Now we can say mathematically that if you shift your time variable by tau and you get exact same joint PDF distribution, then your process is stationary. Now we can simplify this requirement of being strict sense stationary. We have different orders of stationarity. So if you take one instant of time, or if you take only one, if you study the random process at a given time and you study it at a different time and you get the same thing, you don't study the interrelation between them. You just take one time, so it's a first order, and the process does not require a given time. So shifting by one time variable result in the same behavior, we call it stationary in the first order. Okay, so which means that you can take another time, okay, and shift everything, and you get the same response. We can say also that it's stationary in the second order if the relation between different times, it only depends on the time difference. So we can say here, for example, that okay, so we can also look at the mean, correlation, and covariance of a given function. So the mean of a random process is, in general, it's very similar to what we did before in terms of the definition of the mean, but here it's function of time. So the mean could be function of time. If the process has a constant mean, we say that the process is have stationary mean. So if the process itself is strict and stationary, it means also the mean is going to be constant. The mean of stationary random process is constant and it's independent of time. Now if you look at the autocorrelation function, which is the expected value of the random process at two different times, you will find that the autocorrelation is given by the following, and if it is stationary, then it only depends on the time difference. We can also look at the autocovariance. Remember the difference between the autocovariance and autocorrelation? Autocorrelation, we don't subtract the mean. For the autocovariance, because we are studying how the two random processes or the process at different times change or vary, so we subtract the mean. So this is called the covariance, how the two vary together. So we have autocorrelation, we have autocovariance. Now, if we deal with stationary random process, then we can think of the process of only depending on the time difference, and we say that the covariance equal to autocorrelation minus the mean square. So this requires two things: that the mean is constant and the autocorrelation function is function of time difference, which means we have wide-sense stationary random process. Okay, so all strict-sense stationary random processes are wide-sense stationary. However, not all wide-sense stationary processes are strict-sense stationary. That's logical. And we also can say that for Gaussian random process, it's a special case. If you know it's wide-sense stationary, then you automatically can conclude it's stationary in the strict sense, because for Gaussian random processes, it's only defined by the mean and covariance. The two are stationary, and everything else is going to be stationary. So you can think of this as a special case. Properties of the autocorrelation function. The autocorrelation for a stationary random process X is given by the following. And if it's stationary, we can think of the highest value is when tau equal to 0. So the autocorrelation always peak at 0. And because you are comparing a signal with itself, when the shift equal to 0, you get the highest possible value. And that's equal to the mean square value of the process, because what you get is the expected value. Once you put tau equal to 0, you get the expected value of x squared, which is the mean squared value of the signal. Also, it should be even function, because if you compare today with yesterday, it's like comparing yesterday with today, so it depends on the time difference only. So r tau equal to r minus tau. That's an even function. We also mentioned that r0 is going to be the mean squared value, and also it's going to be the peak. So if you take the square value, if you take rx at 0, it should be greater than any other value, being positive or even negative. So I just want to highlight that in some books, wide-sense stationary random processes are referred to as a stationary random process without distinction. We refer to sometimes the autocorrelation as r sub x. X, that's the more detailed expression, because we are comparing x with itself. That's auto. When we say auto, we are comparing things with itself. But to be short in notation, sometimes we just write x, rx, which means rxx. Let's look at this example. Show that the random process where A and Fc are constants and theta is uniformly distributed between minus pi and pi. This is just a mathematical representation of a uniformly distributed between minus pi and pi. Is wide sense stationary? Is wide sense stationary random process? There are two conditions that we have to test. First, we need to make sure that the mean is constant of this random process, and the second thing is we have to make sure that the autocorrelation is only function of time difference rather than specific times. So in the next slide, I'll just go over this solution. So the process which is given here, remember that these are just constants, and theta is the only random part, and it's a uniform. We can rewrite uniform in this format. It's 1/2 pi constant over the period from 0 to 2 pi. How do you find the expectation? You multiply the PDF, which is 1/2 pi in this period, by the random process, and we integrate. You know that if you integrate a cosine and theta goes from 0 to 2 pi, then the average is going to be 0. The cosine will have an average of 0. We can also find the autocorrelation at two different times, at t and t plus tau, or if you like t1 and t2, which is nothing but the expected value of the random process by a shifted version. Cosine times cosine is 1/2 into cosine the sum plus cosine the difference. Now luckily the expected value of cosine, where theta changes from 0 to 2 pi, this is not even just one period, it's two periods because we have to double the angle. But that's great, because if you integrate cosine over two periods, you are still going to get 0. So this is going to cancel out to 0, and what remains is this term. So the autocorrelation is only function of tau, which is the time difference between the two. So this concludes that the process is in fact wide sense stationary. So it doesn't have to be 0, by the way. It could be any constant. So the autocorrelation is function of the time difference, and here we go. The cross correlation is when we have two random processes, x and y. Remember that the autocorrelation function is from the variable to itself, rxx or ryy, at two different instances of time. We can call them t1 and t2, or we can call these instances of time t and u. These are just random, these are just dummy variables. The two cross correlations, we can have rxy or ryx, where we take the expectation of the product. An example for that, if you look at the quadrature modulated process, now we are taking examples which are related to communication. Let's see, what if we have one random process modulated by cosine, another one is modulated by sine, and there is a phase difference. This phase shift is uniformly distributed between 0 and 2 pi. How do you find the cross correlation? We take the expected value of the product. And remember that here I am just coloring them, so you know that the first process is the green, the other one is the blue. So we could have t1, t2, or t, and the shifted version of tau. So tau is the time difference between the two. If we substitute now, the green part represents x1, blue part represents x2, and we can now use trigonometry. We know that sine times cosine times sine, we can represent this as 1/2 sine the sum and sine the difference, with a minus sign here. And remember that this product is nothing but the autocorrelation of x. Now again, the expected value, if you integrate over 2 pi, you can tell that this term is going to be 0, and what remains is this quantity. So the autocorrelation after between two processes multiplied by cosine and sine is the same as the original, but scaled by -1/2 and then multiplied by sine, depending on the time difference. If tau equal to 0, then we'll get 0, because cosine, if cosine and sine are orthogonal, we'll get exactly equal to 0. But if tau is any other number, we'll have a different correlation, cross correlation. We can also think about other examples. If tau equal to 0, if there is no time difference, then we are comparing orthogonal processes, which orthogonal means they are shifted by 90 degrees, and the expected value of the product is going to be 0. Here is a summary of the summary of correlation and covariance. We know that the moment or the mean is the expected value of the random process. The autocorrelation, auto means you are comparing the process with itself. And then we have the autocovariance. It's it's a central moment where you subtract the mean. So you want to see how things vary together. If you increase one, what happened to the other? So this is R, this is C. Then we have the cross correlation. And we have the cross covariance. The variance means we're going to subtract them. We can simplify things as we have here. And this is just a quick summary or recall of what we had before. So if you want the details, you can go back to our slow videos on random processes, stochastic and random processes for electrical engineers or for engineers in general. Okay, then we can also look at the ergodicity. Now we can think of the expectation or ensemble averages of a stochastic process are averages across processes. If you have, for example, the weight of one student, the weight of one student, the weight of another student, and you take the cross, if you take at one instant of time, these are the averages. These are the ensemble averages. But we can take only one student and look at his weight versus time. This is called the time average. If the time average is equal to the expectations or the ensemble averages, then we say that this process is organic, which means taking one student across time is like taking all students. The example of weight is not ergodic, of course. But for example, if you look at the body temperature, maybe taking one student will be a representative of all students. I mean, assuming they are all healthy. So here is the definition of the expectation or ensemble average. And here how we look at the time averages. You integrate over a certain period of time and you divide by that time. You need to cover the entire process. So this is why we have the limit at t goes to infinity to get the exact time average. Now we just explained the meaning of the ergodicity, and I'd like to share with you now the relation between different levels of ergodicity. If all the statistics are ergodic, we say that this process is ergodic. But it could be ergodic in the mean, which means just the mean in time equal to the mean or across the samples. Or it could be ergodic in the autocorrelation, or it could be just ergodic in the strict sense. And I'd like to share with you that the following diagram. So we have wide sense stationary processes. Then we have a second order, which is more strict requirement. So if it's second order, it's automatically wide sense. Then we have strict sense stationarity. And then we have ergodic or fully ergodic. So for the process to be ergodic, we know that it's automatically, the process is automatically wide sense stationary or stationary in the strict sense. Here is the example that I just mentioned regarding the student temperature and the student weight, assuming that all students are healthy. Another examples, another exercise for ergodicity. This is an exercise, so I'll leave it for you. The process, the requirement is to show that this process is ergodic, in fact, in the mean and autocorrelation. So you need to find, we have found the mean and the autocorrelation, the ensemble one, and you need now to do it in time. The last example we'd like to do is the random binary wave or pulse. As the name suggests, this pulse is either +1, +a, or -a. So the pulse are represented by plus or minus a volts, and of course the mean would be 0. So for every period capital T, we have either +a or -a. In general, we don't know the starting point, so we have a delay Td. This delay could be anything within the bit duration, which is capital T. So we can say that the PDF for this T is going to be 1 over T within capital T, and it's going to be 0 outside. This will guarantee that the area equals to 1. Now we know that if you compare two signals outside, if you compare the signal with itself after shifting more than T, then we know that the answer would be 0, because it's random, could be plus or minus. If you multiply the signal by a shifted version of it, and the shift is more than T, then you get 0. Now next we'll see what happens if the shift is less than t. Of course it depends. If the shift is 0, we are comparing the signal with itself and we get a squared because we are multiplying the signal by itself. As we go away from, as we increase the delay up to capital T, then we see a reduction in similarity. We can do this by looking at the exact math and the multiplication between the two. But if we just consider the basic concept here, you're looking at the expected value of x of t times x of t, two-timed version, and we have a scaled version by the probability, because we have to we have to look at the expectation of all possible value of td, and then of course we'll get the linear operation and we get the following triangle. It's logical because it says if you are comparing at 0 time you get a squared, if you are beyond t you get 0, and whatever is in between we have this decay. So if you want to receive the signal, if you want to compare it with itself, we have high correlation if we have the right delay, and once we exceed 1 bit delay, then there is nothing that we can say about the bits. Okay, I also did this example. That's the exact mathematical representation of the sketch. I also did this with MATLAB. So I'm sharing with you the following MATLAB code, which is nothing but an implementation of the previous example. I would be sharing this with you so you have access to the code. Here's the pulse shape generated, and here is the correlation. Remember that we have to do this in a loop. If you need to find the expectation. You don't just do one example, you have to keep generating different delays. That's a quick summary of random variables, and we'll see you in the next video.